Let's get started.
Okay, so I feel kind of apologetic about it. I feel like I did a fairly poor job presenting Hamlet slides, but on the other hand, I think I presented you with enough pieces of the puzzle to put them together. I don't want to continue to rehash confusion. I think it's, I've certainly stated clearly what Hamlet slides are in dimension 3 and 4, and I think I gave you a pretty clear picture of why Hamlet slides are what occur when you have one parameter family, when you see the descending manifold. You have two critical points on the same index. You look in a level set between them. You see the descending manifold for one of them and the ascending manifold for the other. You see them be disjoint and then cross at one point of intersection and then disjoint. And that crossing is transverse in the time direction, in the sense that it's a crossing, and it's a crossing like this, not like that. They don't touch and bounce, right? And then the other the key observation to get this pair of pants thing was to say, well, when one's, this is the descending manifold for something, this is the ascending manifold for something else, they cut across and keep going, you can think of this thing is standing still and this thing is moving, and you can think of this thing as, rather than cutting across, you can think of it before and after co-bounding a surface that also includes a little disjoint linking circle around that. And then that surface that the thing shoots out, co-bounds, is precisely the pair of pants. And because that pair of pants is disjoint from the ascending manifold of the lower critical point, it can flow all the way down to the level below it, and you can see the pair of pants below it. And that's the key idea. What else? So I've been a little bit dishonest in the sense of saying, well, just the same thing works in arbitrary dimensions and arbitrary index. I think that's true, but there's a lot more details to be written down, but I won't do that. The other thing I've been a little dishonest about is I started by saying we're going to consider a fixed Morse function and a varying vector field, or varying metric. And then I sort of started pretending like the Morse function and the metric can move. And for that, to go between the two, what you really want is a little lemma that says that if, I'm going to try to say this fairly carefully, if f sub t of x is 1 is a smooth, just given this, given it's a one parameter family, and such that f sub t is Morse with Morse for all t with distinct critical values for all t, which, depending on your taste, you may include the definition of Morse with distinct, but just to be clear, critical values for all t. So this means, what this means is Morse for all t, which means if you have a critical point at some time, you can follow that critical point. So you can say, I labeled this critical point p at time 0, and at time 1/3, I know where p is, right? I mean, it's moved around in the manifold and its image is moved. But because I don't have any bursts or deaths or anything, I just have the critical points are discrete set, and they remain a discrete set, so you can follow any given one, okay? And they don't cross, so the critical values, you can keep track of the critical values. So you can, whatever critical values you have at the beginning, you can identify the critical values at the end, right? Then what I want to do is say that then there exists a two one-parameter families of diffeomorphisms. So I'm going to have a phi sub t from x to itself, to x, with phi 0 equal to identity, and c sub t from 0, 1 to itself. Anytime I have a manifold with boundary in a diffeomorphism, I'm assuming it's sending a diffeomorphism back to itself. And so, again, so these are what I would call ambient isotopies in the domain and range. Okay? Then, such that f sub t can be reinterpreted as, I want to say it's obtained from f sub 0 by doing something. So f sub 0, I want to precompose it with phi sub t and post-compose it with C sub t. And so the upshot of this is up to ambient isotopies of domain and range, nothing really happens. Okay? So the C sub t is a little easier to think about.
These are different t's?
These are all the same t. Okay? So the idea is that if you want to know what the Morse function is at time t, it's really just the same as the Morse function at time 0, except you move points around in the domain and move points around in the range. You squish stuff around. Okay. So I mean, it's a simple. You might just have something where you look at the images of them. So this is t, and this is the value of the function, p sub f sub t, right? Then you look at a particular critical value, and it wiggles up and down. Okay. If it wiggles up and down, then then the c sub t should be some ambient isotopy that moves that point, straightens that line out, right? So if after I apply c sub t, then I should get just a straight line for that critical value. Okay, that's just, and then what does phi sub t going to do? At the very least, like I've got a critical point, will also move around in the manifold, but it'll then, straighten that trajectory out so it stays still. Okay. I'm not going to prove this lemma. I've talked about it a little bit with Eric. I've written down a proof of it once, which requires a parameterized Morse lemma that we'll talk about at some point later. I don't think it's too hard of a time fitting, but this is sort of, the intuition here is as long as you don't have crossings, and as long as you don't have births and deaths, nothing really interesting happens. We might talk at some point later about how to use this, but the point is then, if you have a one-parameter family of function comma vector field, you can sort of reinterpret that as you can pull everything back by phi sub t and c sub t, right? And reinterpret it as just the function staying fixed and the vector field moving around. So another way to say it is f sub 0 is equal to whatever it is, I'll call it c sub t inverse. And this allows you to, as long as you don't have crossings or anything else, to reinterpret the function as, so you would take your vector field that's moving around, pull it back by these two functions, right? And then you get a new vector field. Actually, you only really pull it back by this function, this domain, and then that'll get a new vector field that's moving around while this thing stays still. So this allows you to, this allows us to assume that one family of f sub t, d sub t, actually the f sub t is constant. T, well, what if there's crossing? What if the critical values cross? Well, then what you want to do is then say, well, we'll talk about critical point crossings shortly, so unless we have crossings over the deaths, which I'll be talking about soon. I'm talking about a lot of stuff which, I think is really not written down anywhere in the literature. Right? A lot of people wave their hands about it, and I'm waving my hands about it as well, but trying to be a little bit more say some things more precise. So one thing you could do if you want to understand what's happening at a crossing is you could try to, I'm going to talk about lowering and raising critical values shortly. You can set up a standard model for what it means to lower a critical value, right? So if I have a critical point, I can create and I want to move it down to, move its value down by epsilon. I can write down a standard model for a one-parameter family that moves it down by epsilon. And then what we want to say is that we can, if there was something where I had a crossing, something went down, I could reparameterize things so that it actually was that standard model. And the vector field wasn't doing anything interesting. Particularly, you don't have any new intersection points between ascending and descending manifolds. So at crossings you don't have, so crossings are critical values. What we can do, we can assume that I want to say F varies, F changes, but the vector field doesn't change. That's not quite right to say the vector field doesn't change, because if the critical point is, that's not quite right. But what we can assume is that in a epsilon time neighborhood of the crossing time, we have no, I'm just saying no changes in the intersection behavior of ascending and descending manifolds.
You're assuming that a crossing does occur there?
If there is a crossing.
If there is a crossing.
Yeah, at crossings, at a particular time when a crossing occurs.
Because it's not always true that.
There may not be any crossings.
And if you pick two sort of consecutive critical values, it's not necessarily true that you can make them cross.
That's also a good point, yes. Critical values, you cannot necessarily make
There's
critical
like
values
this
cross.
condition on the indices.
That's right. And we're going to get there. I'm going to talk about making things, forcing things to cross later. So, I think that's all I want to say about that. Okay, so I want to now talk more generally about what happens in one-parameter families. There's two other things that can happen. I mean, there are lots of things that can happen if you look at, if you look at critical points of index separated by 3 or something. All kinds of behavior can happen with how their ascending descending, how the intersection of their ascending descending manifolds change. What we've seen is that we were studying the case where I have two critical points of the same index, and then we discovered that at isolated times you may have an intersection between their ascending and descending manifolds, and then that disappears again, and then a level below both of them, we have this discrete change. The other thing that is worth commenting on is if the index of, so I have f of p, two critical points f of p and f of q, one less than the other, and the index of q equals the index of p equals 1, then we might in general expect, for at any given time, we might expect intersection between the ascending for q and the descending for p. And then we considered, so now we consider some time varying vector field, gradient like vector field, giving us, and remember I had this notation, giving us this, these ascending, I used blackboard bold for the ascending manifolds and descending manifolds sort of over time. So remember, these were inside 0, 1 cross f inverse of y. So these are just, this is a sphere moving around, and y is between f of p less than y less than q. Okay. And so y is between, it's a regular value between p and q. We look in that level set, we look as time changes, we sweep this ascending sphere moves around, sweeps out some sphere across I, and this descending sphere moves around, sweeps out some sphere across I, and at a fixed time, we expect these to intersect. We expect these in general to intersect in something zero-dimensional. So over time, we expect one-dimensional intersection, right? So we get this blackboard bold intersection. This is a one manifold. So it can do a couple of, if we can look at the points of intersection between the ascending and the descending, and of course you might just have a bunch of points and they just wander around and end up in a bunch of points. But the other thing is you can have 2 points come together. You can have, so if you look just abstractly at time 0, so at t equals 0, to t equals 1, you can have just a bunch of points move around. This is a completely abstract picture. This is just in x, I guess, in 0, 1 cross x. But you can also have 2 points of intersection come back. Right? So what happens when this happens? Rather than trying to do the full general case, I'll just give you an example. So an example for this. And I think it'll be much clearer We'll do the example just in, let's do n equals 3 again. So we're going to draw pictures in a 2-manifold, and we have a index, let's say index of p equals 1, and index of q equals 2. So then we've got a, we had a handle diagram. Of course, we could be looking at Haggard splitting, but let's not think of a Haggard splitting. Let's just think of a simple handle diagram they first started with the 3-manifold. So I draw things in the boundary of the 0 handle. I would draw the descending 0 sphere for this index p critical point. It would be a pair of points, right? But really, I would thicken them up to be disks. Okay. So this is the just p to p. And that's not really the point P, right? That's the descending manifold for P, right? Now, what you should think now is that there's a, I'll draw the 3-dimensional picture on the side here. There's really the point P, and there's this descending manifold. And descending manifold. Ascending manifold. And now I've got, now the point is what I want to have is Q, I want to look at a situation where I have 2 points of intersection between the ascending manifold for P and the descending manifold for Q, and I want to see them disappear. And now that's, if you start thinking about it that way, it's not too hard. So I might have the descending manifold for Q widths. Okay, so that means that over here in this 3-dimensional picture, on this picture, the descending manifold for Q is coming, picture. Just draw that bigger. P right there, and then I have, I won't try to draw the 3-handle, I'll just draw its descending manifold. The 2-handle, it comes, you know, somehow, its descending sphere goes up and over, and down the other side, and then walking around, up. And that's the descending manifold for Q. Okay, and so there's the 2 points of intersection between the ascending and descending manifolds right there. And now, so what's the obvious thing to do? The obvious thing is to try to simplify it by pulling this finger across, right? So it's across there, so you just pull this back, and when you pull it back, you will get a new picture. This one, a new picture here. And this comes up and over, and it's a little tiny thing, and then that shrinks all the way down, and you eventually get. You'll have this that particular point. This point here will be exactly when that grid point touches right there. Have the descending manifold touch your tangent, and then finally. It's just disjoint. So this is. Any questions about that? That's generally what's happened. So you have pairs of critical points, pairs of intersections between ascending and descending manifolds canceling together, right? And simplifying the picture. Or of course you could have the opposite move where a finger goes over and creates that. And you can have, so it's not hard also to see that if you do this move, you can construct the 1-parameter family to realize that move as a 1-parameter family of Morse functions, or recreating vector fields, and then therefore, if you ever do that move to a handle diagram, you're not changing the manifold. Of course, remember what's really going on. You should visualize some kind of 2-handle that's going up and over. Right? So that's like, it's like this solid 1-handle, and then I've got a little covered bridge going over the top of it. That's all I want to say about that move for now. I think that move is sometimes called a finger move, because it's like a little finger sticking out over the handle, but I don't know how universal that is. This is an issue in the proof of the H-cobordism theorem, which is this high-dimensional theorem that about simplifying cobordisms. And one of the key steps is, if you notice pairs of intersections like this, you want to try to get rid of them. Okay? And if you have enough algebraic data to get rid of them, what you sort of see is there's a little arc in this ascending manifold, and there's an arc in this descending manifold here, and then you want if those two arcs together bound a disk, an embedded disk, then you can do this finger move to push this back and simplify your picture. What happens, so in high enough dimensions, if you have a loop, these two arcs form a loop. If you have a loop that is homotopically trivial, in high enough dimensions, so that means it'll bound a mapped-in disk. In high enough dimensions, a mapped-in disk can be made embedded. In dimension 4, mapped-in disks can not be made embedded. And that's why the proof of the H-cobordism theorem breaks down in lower dimensions. So there is this funny thing that happens in dimension 4 where maybe that disk then has self-intersections, and you try to clean that up, and you get towers of sort of disks that you're trying to back in that are horribly self-intersected, and that's just the tiniest hint as to why you might be able to do something in the continuous world that you can't do in the smooth world in dimension 4. It has to do with, you try to embed a disk, it intersects itself. You find some point of self-intersection, you find a loop around it, you try to have that loop bound a disk. That loop intersects it, that disk intersects itself. And you keep going, and then you can do some kind of limit, which ends up producing a continuously embedded disk that's not smoothly embedded. But that's far afield from what we'll do. So now, what else happens in families of Morse functions? Okay, so the first, so now let's say, let's be a little careful. So I'm giving F0 and F1 two Morse functions. The first thing you might ask is, can you connect them? Is the space of Morse functions connected? Can you connect them by F sub t, which is Morse for all t? There's some obvious obstructions, like for example, they could have different numbers of critical points, right? And you just solve critical points. If it's Morse for all t, you just have critical points. So obvious answer is no. You could say, what if they have the same number of critical points? And then it's sort of an interesting question. But still, the answer is no. But that's much harder to show in general. But if you don't allow crossings, well, that again depends on where you want to go. You can ask this question depending on, but the basic answer is no. And so you can say, now suppose you choose, but they are functions, right? They are maps to, well, we're not going to map to the circle. We're mapping to the interval or to R. And if you think about it, maps to R, any two maps to R are homotopic because they're all homotopic to a map to a point. It's not a Morse function, it's still a function, right? And if you're mapping to the interval, if you have a cobordism, and as long as you map the bottom to 0 and the top to 1, as long as you map the same parts to 0 and 1, again, any two maps will be homotopic. So let me say that carefully. If X is a cobordism from N0 and 1, and F0, F1, map X to 0, 1, respecting the cobordism structure. So that just means F0 inverse of 0 is M0, F1 inverse of 0 is M0, and so on. Okay, then there will exist some one parameter family, F sub t, from X to 0, 1, which at least respect the coordinate structure, but they may not be Morse functions. Okay? Not necessarily Morse, but still respecting a coordinate. So they still send, they'll still take, you can think about why that's true. It's not that hard to see why that's true. Of course, if they start switching around the endpoints. So you do need, one thing you do need to use here is the existence of collar neighborhoods and boundaries. You can fix that up. Okay. But anyway, the point is, we can get these families, and if we're just mapping to R, it's even easier, right? We have a closed map, we're just mapping to R, just make everything homotopically to the point, and we're done. So now, what can we expect? So the theorem, let's just make a definition. Yeah, I'll actually, there's terminology that, well, it's just definition. F sub t is a generic homotopy. So this is a bad definition because the word, what you should really do is define a property and then show that that property is generic. And I'm saying, here's the property's name is generic, but really what's encoded in that is a statement that the following property is a generic property. Is a generic homotopy if, for all t, let's see, for all points, it's going to look just like our definition of a Morse function. For all t and for all points p and x, there exists, best way to say that is there exists local t coordinates. Let me say for all t0, t0 and 1. I'm assuming my parameter, my t is going to t0 and 1. There exists, let me call it tau. There exists local coordinates tau around t0. It seems funny to put coordinates around the point in the interval, but we can, just reparameterize things a little bit. And t-dependent coordinates around x. And t-dependent coordinates, so these are going to be x, I'm sorry, around the point p, it's going to be x1 to the t up to xn to the t, and t-dependent coordinates, let's say y sub t, around f sub t0 of p. You just start sort of guessing what we're going to do. We're going to sort of say it looks standard with respect to these coordinates, but the coordinates are allowed to vary in time. The coordinates in domain and range are allowed to vary in time, and the way that things vary in time. I could just as well make these dependent on tau. Let's put a superscript here. Let's make this tau just because everything varies that way. I mean, tau and t are equivalent. We're just using them to parameterize something. Such that f sub t has one of the following forms. Local form number one is, actually, yeah, local form number one is there's nothing, no critical value at all. So f sub, it's of the form, I'm going to not write the superscript, so it's x1. I'm just going to write the value. So it's just x1. This may seem a little bit funny to say that the function is just x1. What I mean is there's no critical points, right? Anytime you have a function at a fixed time with no critical point, right? Then you can, using the inverse function theorem, you can rewrite it as just there's a coordinate in the domain that's mapped to a coordinate in the range, right? So I could have, so this just means, you know, so I can find, and there's no critical point for a short amount of time, right? So as time varies, there just persists being no critical point. The second thing, though, is just sum of squares, right? So it's minus x1 squared minus xk squared plus x1 squared n squared. So this means that as time varies, it just looks like a Morse function. And there's still no time in here, right? We've swallowed up the variation in time into how these coordinates depend on time, right? And then the third thing is the x1 cubed minus tx1, and then we go minus x2 squared. Actually, let me write it differently. So let me know. I'm going to go minus x1 squared minus dot 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 minus xk squared plus, put another line here, xk plus 1 cubed minus txk plus 1, and then plus xk plus 2 cubed squared plus dot 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 plus xk squared. So, you know, pay attention to that in the case where n equals 1 and k equals 1, in which case these aren't here and these aren't here, and this is just the x cubed minus tx.
For the second one, where as t varies, we can't change index.
Correct. The index can't, because index is a discrete thing, right? It can't jump. I mean, this is the only thing where, maybe I should call that tau. Right, to parameterize t, reparameterize the time variable. So, you know, I need to reparameterize the time variable because it's going to happen. The event when it's not Morse happens at time 0, right? And notice that when time is, I put a minus sign, so when time is negative, this is a plus, so the derivative of this is positive, and then we don't have any critical points at all. And when time is positive, I have 2 critical points. Because, we won't do the calculation here, but if you just focus on, if you just look at the xk plus 1 plane, and you look at xk plus 1 cubed minus tau x equals 1, that you either have something like this. So as soon as you have one coordinate in which there's no critical point, then there's no critical point period, because you're only mapping the dimension 1. So this is tau negative. You have this tau equals 0, and this tau positive. And when tau is positive, you could, you know, as soon as tau is positive, you could change your mind and get these kind of coordinates, right? Where you'd have to re-coordinatize so this is your maximum. So then suddenly, in the xk plus 1, it would look like minus xk plus 1 squared, right? And so minus xk plus 1 squared means you'd have an index k plus 1 critical point. Over here, it would look like an xk plus 1 plus xk plus 1 squared, which means you'd actually only have k negative, right? So this means that you draw in this picture, the surf graphic, which is the graph of critical points we see at time t equals 0, and we see precisely as well. We see a pair of critical values appearing. I guess they'll be there at the origin as well, but any given point, and this is index k, and this index k plus 1. Okay. So this is what we will call a generic homotopy. So it's either you just got a Morse, it's nice and Morse, you know, there's either no critical points at all, or it's got a single Morse critical value, but then you can suddenly have this birth canceling pair. So this is a birth. Notice I didn't say that these coordinate charts were orientation preserving. So therefore, of course, my tau could reverse orientation in the time direction. So I'm also allowing for deaths, right? Birth. Canceling pair. And so the theorem that I'm still deferring, and it's in the same line as the Morse lemma, and proving that Morse functions are stable, is going to be that generic homotopy are generic and stable. One, stable. Stable means if, as a homotopy, you wiggle it, it will retain this property. And two, generic. Generic means that if you're given a particular homotopy, you can wiggle it a little bit and it will become like this. Okay? This is spoof deferred, or I may just give you some references. I want to give the one reason I'm deferring this and the other, the more basic thing that Morse functions are generic and stable, is that I want to try to deal with them in sort of all at once when thinking about singularities, differential mappings, and I'll just give you some references, but I don't give you details. But I want to show you how it's kind of the same type of argument. But it's the least believable, right? Somehow once I've got a new time parameter, only cubic things occur as so if you had something that seemed to involve fourth degree, you could split it up and perturb it into degree 3 parts, but it doesn't. It's hard to imagine how you could get this cubic behavior to be something a little bit smaller degree. But I want to look at the consequences of this more than anything else right now. I want to look at the consequences for handle decomposition / handle diagrams. Okay. The key observation is that in local model number 3, what do you have? You have, if we can, I want to think about the ascending and descending manifolds, right, for the new pair of critical points, or if we're going the other way, the old pair of critical points. And so, first of all, if we let v equal v sub t, so this is now a function f sub t. Where the v sub t equal the standard Euclidean gradient for f sub t. We can actually think about that gradient vector field kind of very explicitly, because the nice thing about the Euclidean metric and these functions is they split out coordinate by coordinate. Right? The gradient vector field is just going to be the gradient in the x1 plane, gradient in the x2 plane, etc. So then we really only have to understand the gradient vector field in the xk plus 1 plane, and it's precisely right here. It's just what it is once you have a pair of critical points. Right? I'm doing the downward flow for the gradient vector field. And so I claim that, so you get ascending, let's call our two new critical points. I want to understand what happens with the ascending and descending manifolds of the critical points. So let's call it P sub, what you really call it, I'll just call it P. It's going to sort of move around the manifold, but be the index k critical point, q index p plus 1 critical point. We've generated these two new critical points. And I mean, it's useful to stare at this picture and say, well, how does this, how how should I interpret this picture as something higher dimensional, right? Well, the thing is that I've got k other directions, and then n minus, I've got the negative directions and the positive directions. So all that means is if we just, this is a slice of this picture. If we include into this slice one of these 1 up to k coordinates that say comes out here, then in that coordinate everything goes down. Okay, because I've got a minus x. So if we drew, for example, the x1 xk plus 1, for the graph of this function, the x1 xk plus 1 direction, then it's minus x1 squared. So here I'm going to have something descending and something descending, right? So now then you see this is index 1 and index 2, right? And what happens to the ascending and descending manifolds here? Here's this ascending manifold, here's this descending manifold, but the ascending manifold is just an arc here, right? And the descending manifold is a ball on the intersection, a disk on the intersection of the point, okay? If you include these coordinates instead, you can always sort of pick which one you want to include and still get a three-dimensional graph, then everything, this goes up and this go up, right? So, but it's not too hard if you just think about that to see that. So the ascending D manifold for P at some level Y intersected with the descending manifold for Q at the same level Y, where Y is some regular in between, is going to equal 1, 1. And at that point you can work out precisely what it is from this picture, but I mean, you can make the way you coordinatize everything's at level 0. And so at that level 0, you get that 1 point of intersection. So to characterize what happens is you create a new pair of critical points where the ascending manifold for one and the descending manifold for the other intersect at a single point. And the example for that in dimension 3 is, this is back to the convertible roof now. Example. Here's handle attachment for P, and now if I want, and then Q just goes over once. So that's the attaching sphere for the index, index 2 critical point, and if we want to draw it three-dimensionally, something going up and over. So here's the belt sphere for critical point P, and then the attaching handle for the critical point Q. Like this, and then there's the handle, pick it up, and somewhere inside here is Q, and there's your single point intersection. Okay. Now, we sort of had this rough idea. It's not that hard to prove. Without Morse theory at all, you can prove that if you have a handle and a handle of higher index whose critical points such that the attaching sphere for one intersects the belt sphere for the other at a single point, then topologically you can just cancel. So if you attach a K handle and then attach a K plus 1 handle so that the attaching sphere for the K plus 1 handle intersects the belt sphere for the K handle at one point, then you produce a manifold that's diffeomorphic to what you had before you attached either of the handles. Okay. In Donnford-Stipschitz, there's a non-Morse theory proof of that fact. So Donnford-Stipschitz, I don't know if I've ever written the name of the book out. It's four manifolds in its name. I can't remember what it's called now. But in this, there's a non-Morse theory proof that this cancellation happens. But we can also, what I want to do is actually show you that I would like to, so this is, what I'd like to do is run this backwards, right? Say that suppose I see two critical points with a single two critical points in consecutive level sets, right? So there's no other critical values between them. And I find a single intersection between the ascending and descending manifolds and no others, exactly one, then I want to argue you can actually modify the Morse function so as to cancel those two. And so the claim is okay, so well, okay, the first thing is, if you just were given a one parameter family of Morse functions, then we sort of now, and with gradient vector fields, and want to understand how the handle decompositions change, we know that the handle decompositions change by handle slides, and now this other event, which is a birth of a canceling pair. This is a canceling pair of handles. Okay. And the other thing I want to say is that if I take the handle decompositions and I do those moves on them, we know that if you do a handle slide, then you can follow that, you can construct a one parameter family of Morse functions that achieves that handle slide. And I want to argue that if you see a pair of handles that behave like this, then you can construct a one parameter family of Morse functions that cancels those two critical points. So the next claim is that given let's say F and the gradient line vector toward V, and then P and Q at above. So P and Q such that P less than Q, index Q equal index P plus 1, P plus 1, and the descending manifold for Q at level Y intersecting the ascending manifold for P at level Y at 1 point. Then there exists some F sub T canceling P and Q. So, and I mean, again, even that's not very carefully stated conclusion. What I mean is there's an F sub T which has one singular event, and that singular event is that those two critical points, it has a local model like this. Everywhere else it stays Morse, and therefore we don't do anything to any of the other critical points. And so I also want to assume here that, so buried here is the assumption that no critical values between F of P and F of Q. And this is something I've been sort of tacitly assuming all along, and that's another thing we have to be careful of. You know, suppose they're much farther apart, there's lots of other critical values and you want to cancel them. You really have to move them down until they actually don't have any critical values between them. Because you know if you're going to do this cancellation, they have to get very close to each other, right? So in order to do that, that's sort of the next thing we want to talk about, is how can we move things close to each other. But let's finish this discussion first. So let me just sketch why this is true. Really not sketch why it's true. Let me say in words what I wanted to do and do it next time. The idea is to the idea basically is going to be, I've got this, I think about if there's a single critical point of intersection, that means there's a single flow line from one to the other. And so that gives me a descending direction from the higher one, and an ascending direction from the lower one that line up. And what I want to do is I want to make it look just like this local model. So that's, I'm going to want to pick out my coordinates around both of them so that this ascending direction, this descending direction, are actually the k plus 1 coordinate. So I want to boil it down to a slice in which I see that single flow line between them, and then say everything else I've got something going up and something going down, and then inside that slice I've just got this. I've got a complete local model in which I see something. You know, basically I want to say that there's a certain slice across it in which this is all I see, and once that's all you see, then you can just wiggle it to look like